Okay, hello, Precalc C. I thought we were going to get to this on Thursday and Friday, but I guess not. Continuing, and in fact sort of finishing our review of inverse trig. I thought we'd do one of the problems for homework that you had was number 7. This was just pretty hard. The problem said, what is the secant of 2 arc cosine negative 4/5 plus arctan 8/15. Okay, this is just a big, disgusting problem, and okay, it's not objectively important in and of itself, but it is good practice with several important topics. So, okay, how do we even begin this problem? Well, I think the first thing to do is to recognize that arc cosine of negative 4/5 is some kind of angle. So for purposes of simplicity, let's just abbreviate that angle alpha. And let's take arctan 8/15, that's some kind of angle. Let's just abbreviate that beta. Okay, so then there's just sort of less writing to do, I guess. And what we really have here is secant of 2 alpha plus beta. Alright, and well, alright. Just check this, yeah. What is secant 2 alpha plus beta? Well, I don't really have a formula for the secant of a sum, but of course the secant is just the reciprocal of the cosine. So really this is like 1 over cosine 2 alpha plus beta. And what's that? Alright, well I have a formula for that, and this is one of the sort of important formulas that you should all just kind of know by heart. Basically, which is cosine of a sum. It's one of the formulas from which you can sort of derive all the rest. And okay, well, I just do know that cosine x plus y is cosine x cosine y minus sine x sine y. So I will continue to simplify this as 1 over, this becomes cosine 2 alpha cosine beta minus sine 2 alpha sine beta. And okay, cha-cha. And I guess there's still more work to do because, well, what is cosine 2 alpha? There's a bunch of different formulas for that, or there's a couple different ones at least. But maybe the simplest one to do is just cosine squared alpha minus sine squared alpha. That's actually the one that you get sort of directly from the from using the cosine of a sum formula. Yeah. So if you just think of this as cosine alpha plus alpha, then you get cosine cosine minus sine sine. So this is kind of the most direct formula, so to speak. All right, and then another thing that everyone should know is sine 2 alpha, which is 2 sine alpha cosine alpha sine beta. Okay, so basically, so far this has just been an excuse for us to practice our memorized, I guess, trig identities. But another thing that we are doing is practicing our understanding of the inverse trig functions. So now, I need to, of course, find all of these values. How am I going to do that? Well, I'm going to make a picture of alpha, after all. And, well, okay, well, what is alpha? Alpha is arc cosine negative 4/5. And so now it's just the time for you to know that arc cosine always outputs something between 0 and pi. So if I want the arc cosine of negative 4/5, well, then I need to go into quadrant 2. And so here I am in quadrant 2. I feel we should always be drawing these like angles kind of in a certain quadrant. So, alright, well, that's alpha, and I need to draw alpha such that the arc cosine, such that the cosine of this angle is negative 4/5. And there are an infinite number of ways to do this because there are an infinite number of triangles such that the ratio between the x-coordinate and the hypotenuse is negative 4 to 5. But of course the simplest thing to do is to just call this negative 4 and this 5. Right now you can just confirm that the cosine of this angle is negative 4/5, and so this is a picture of arc cosine negative 4/5. By the Pythagorean theorem, that's 3, and that's that's all I need to know to compute sine and cosine of alpha over here. And then, okay, I'll do the same thing with beta. This one's a little bit simpler. What's arctan? What is beta? It's arctan 8/15. Arctan of something positive is going to be a first quadrant angle. Arctan always outputs something between negative pi over 2 and pi over 2. But here it's positive, so alright, let's see, I guess it's going to look something like that. And that's 8, well, okay, that's that. There's that. And then the angle beta is a first quadrant angle. Note my like sort of rotational angle arrow there. And then the sides of this triangle are, well, once again, I have technically an infinite number of choices, but the simplest thing to do is to consider this whole thing happening on a circle of radius 17, because if that's 8 and that's 15, then that's 17. 225 and 64 is 289. So that's kind of one of those Pythagorean triples that comes up again and again. All right, I'm going kind of too slow here, but that's the picture, and now I just basically just do the problem, right? So this is 1 over, what's cosine squared alpha? Well, it's negative 4/5, so it's negative 4/5, you know, squared, minus sine alpha, which is 3/5 squared. Cosine beta is whatever it is, 15/17 minus, it's gonna take up a lot of space, I see, minus 2. Sine alpha is 3/5 sine cosine alpha negative 4/5, and sine beta 8/17. Okay, so let me just double check all that. It's probably all right. So what is this? Does this stuff simplify at all? I hope it does. This is going to be 16/25 minus 9/25. So that's 7/25. Make sure I did that right. 16 minus 9. So I had 7. I get 7/25 times 15/17, whatever that is. Okay, and now plus this is going to be well. I mean, I guess I can just do it, right? It's 2 times 3 times 4 times 8 over 25 times 17. All right. So now this whole thing has really just been reduced to a bunch of arithmetic, but I'm gonna still finish it off. Maybe I'll go kind of sideways now. What do we get? Oh boy, 7 times 15 is 70 and 35, so it's 105 over whatever 25 times 17 is. I don't feel like doing that right now. This is something, let's see, 1, 2, 3, 4, 5, that's 6 powers of 2. That's 64 times 3, 180 and 12, that's 192, look at that, over 25 times 17. So, this is going to be 1 over 297 over, now I'll do 25 times 17 finally. Well, 25 times 16 is 400, so that's 425. Man, I hope this is right. So final answer, 425 over 297. I think I have an answer key somewhere. Good, that's right. Alright, so that's just one big old problem. Practice with fractions, practice with arithmetic, practice with trig identities, practice with the inverse trig functions. Okay, this is still in the category of easy problems in my opinion because, okay, there's a lot of room for error here, but we're still just sort of computing. I mean, the answer to this after all is just a number. So, the more interesting stuff happens on the next page. I'm not sure if you did stuff like this exactly last year or not. But, okay, we're about to find out. So if you turn to page 5, I told you not to do this yet because we were going to do this, you know, in class, but Zoom school, we just can't get anything done. So we're going to just do it now via video, and hopefully you're watching at whatever speed is right for you. This is number 8, and the problem is, hey, what is tan of arc cosine of x over 2? Okay, this comes up a lot, so on the face of it, this might seem very much like problems we have just done. Because, well, if this x were not an x, but like a 1, for example, then I know exactly what to do. I'm taking the tan of some angle. What is that angle? It's arc cosine 1/2. So I go over here and I draw a picture and I, do some kind of thing such that that's 1 and that's 2 and I have my angle and I do the Pythagorean theorem and I take the tan of it and I'm done. All of that is still true. But now, I don't want to do this for tan of arc cosine of 1/2, but tan of arc cosine of x over 2. So this is basically like a function. In fact, we might as well explicitly write this as a function. Perhaps I did even on your version of this packet. Checking it now. Yeah, I did. On your version of this packet, it does just introduce this as a function, and the directions on your version are, well, express f as an algebraic function of x. In other words, though this might look like a trig function, it's really not a trig function after you finish kind of simplifying and analyzing it. Okay, how are we going to do this? Well, the directions also are there, right on the page. They say, hey, separately consider the case where x is positive and the case where x is negative, making a separate picture for each case, and then give the domain. Alright, well, even if they didn't tell you to do that, you basically just have to do that, because when I tried to pursue my strategy from the previous problem and from the other problems in this packet, I suddenly find that I don't really know what to do. Because if you tell me to draw a picture of arc cosine x over 2, well, I'm a little bit stumped, because it seems to matter whether x is positive or negative, and it just does matter. Knowledge of the arc cosine function says that arc cosine always outputs something between 0 and pi, and therefore, if I take the arc cosine of something positive, well, then that's going to be a first quadrant angle whose cosine is positive, and if you give me the arc cosine of something negative, then it will be a second quadrant angle. Therefore, I must split this up into two separate cases. The case where x is negative and the case where x is positive. So for clarity, I will draw two totally separate pictures, and now I'm going to just solve this problem, twice, basically. Okay, well, here we go. In the first, so there's one chance in which this is a positive first quadrant angle. That's indicated with my rotational angle arrow. And the other case is the one in which this is a quadrant 2, positive quadrant 2 angle. Okay, and well, now I just have to make a picture of the angle such that the cosine is x over 2. Alright, well, if x is positive, I think this is pretty straightforward, because well, I need the ratio between the horizontal component and the hypotenuse to be x over 2. So the simplest thing to do is to just call this x and call that 2. Now, alright, based on triangle similarity, of course, this is not the only triangle this is not the only way to label this triangle. This is the simplest way to label this triangle, because it's just adjacent over hypotenuse and we're done. But if you wanted to be weird or something and call this 3x and call this 6, that would not be wrong, because it's still true that the ratio between the adjacent side and the hypotenuse is still x over 2. And so you really do have some choice, and the thing is that because whatever choice you make, the triangles are similar, that's why it sort of doesn't matter. But okay, in this case, the simplest thing to do is just say x over 2. Hopefully that's clear. Alright, well, if that's the case, then the Pythagorean theorem tells me that this is root 4 minus x squared, and maybe you even want to temporarily kind of name this angle, theta or something like that. I don't know if that's helpful to anyone. So that means sort of we're kind of nicknaming this angle arc cosine x over 2. We're nicknaming it theta for a moment. Well, now it's time for me to answer a question, and the answer to the question is, what is the tan of theta? I think I'll just ignore the nickname and I'll just write it out. What is tan of arc cosine x over 2 in this case? Well, we just read it off the picture, and I get it's that over that. So what we end up with is 4 minus x squared over x. Okay, that was fine. Let's see what happens in the case where x is negative. Well, if x is negative, I have to, use some more care when labeling the sides of the triangle. But I still need it to be the case that the cosine of this angle is x over 2. So if the cosine of this angle has to be x over 2, then I think, again, the simplest way to do this is put the x here and put the 2 here. And this picture is making sense because we are in the case where x is negative. And since x is negative, it's negative, right? So that's why we're in the second quadrant. We should expect the horizontal component to be negative. So all right. So if you trust that picture, and I think you should, then we can just finish it off. This is the square root of 4 minus x squared. Okay, and now what is the tan of the arc cosine of x over 2? Well, it's going to be, okay, it's just that over that again, right? So it's just root 4 minus x squared, because it's just opposite over adjacent, yeah. Okay, so I got the same formula in both cases. Let's just look a little bit deeper at that and see if this, let's just do kind of a quick spot check to see if this makes sense. Here we are, and I have a first quadrant angle. Well, this numerator is clearly positive. This denominator, because x is positive, is positive. And so if the numerator is positive and the denominator is positive, the fraction is positive. Do we expect the tan of a first quadrant angle to be positive? Yes. So this seems just good. Okay, moving over here, what now? Well, the numerator is positive, clearly, because the square root of anything is positive. But x is negative now, so this is a negative denominator. So numerator positive, denominator negative. This makes this fraction negative. Is that the right answer? Yes, because the tan of a second quadrant angle is negative. Okay, so even though we took all this kind of care and efforts to draw the picture twice, it turns out that the answer to this problem is that this is just this. Root 4 minus x squared over x. This is f. Okay, and chop chop. And so that's kind of the final answer to this problem, and that's what they mean by express f as an algebraic function of x. This is considered algebraic because well, it's just algebra type stuff. It's not. It's a sum product quotient of polynomials and sort of algebra-ish things like square roots and stuff like that. So in other words, if you just looked at this function out of the blue, if someone just came up to you and said that this was my function f, I wouldn't think that it had anything to do with trigonometry at all. So that's the sense in which it's algebraic. Okay. Yeah, even like the first month of Precalc C or something, you could have been given a function like this and you could have been asked to analyze it. Well, we have one more thing left to do, and that is to say, all right, what's the domain of this function? Okay, so what is the domain of this function? Well, you have two choices, basically, on how to do this. The simplest thing to do, I think by far, is to use this version of the function. In which it's represented algebraically. And okay, this is just an exercise that you did in Precalc C, where you looked at functions like this and you just said what the domain is. What's one thing I noticed? Well, the bottom can't be 0. That's just a fact. What's another thing I noticed? Well, I can't take the square root of a negative number, so I need x to be not that big. If x is like 1 or whatever, that's okay. If x is 3, that's bad. So x can't be bigger than 2, and it also can't be less than negative 2. So I don't think I need to go into any more details there. I mean, you could, if you need to reason this out, you could say, okay, well, I need 4 minus x squared to be greater than or equal to 0. Maybe some people would find this helpful. So that means that. So I need x squared to be less than or equal to 4. So when is x squared less than or equal to 4? Answer, when x is between negative 2 and 2. Okay, So when you, I guess that was maybe good math to do or something. Some people can just do this in their head in a couple seconds. Well, if you combine the fact that x has to be between -2 and 2 and the fact that x can't be 0, then I'm ready to give my answer that the domain is in fact everything from -2 to 0, union open, so not including 0, everything from 0 to 2. Okay, good. There is, however, another way to do this problem. And maybe it's worth it for some people to sort of do it both ways and see how it goes. Well, and that is to answer the what's the domain question using the original version of the function. So here is my function, tan of arc cosine of x over 2. Alright, so this one is now going to be a little bit tricky because you have to know a lot of things. Well, what kinds of things am I allowed to take the arc cosine of? Well, that's a complicated question, but you know, you've seen that the cosine function, you know, looks like this, and that's -1 and that's 1. So the range, since that's cosine, the range of the cosine function is always -1 to 1. Cosine outputs things from -1 to 1. And therefore, arc cosine inputs things from -1 to 1. Which is to say, it's actually going to look like this. So that's like pi. And okay, we did all this in the other video, so I won't sort of go through the explanation again. But if this is, sorry, it's getting a little sloppy over here. But this is cosine, this is arc cosine. Then I am only allowed to take the arc cosine of things between -1 and 1. Sort of course, because cosine only outputs things between -1 and 1. Alright, so in other words, another way to put it is that the domain of arc cosine is -1 to 1. Well, looking at my function now, if the domain of arc cosine is -1 to 1, then I better be plugging things in here which are between -1 and 1. In other words, x over 2 needs to be between -1 and 1. Just fact. The sort of negative way of putting it is, if this is false somehow, if I try to plug in something, if I try to plug in an x such that x over 2 is not between -1 and 1, then this function will crash, and then that number should not be in the domain of my overall function f. So now to finish this off, you just multiply by 2, and this tells me that x has to be between -2 and 2. So this is a sort of a totally different way of arriving at this kind of fact over here. But, of course, we're not done, because numbers between -2 and 2 are precisely those numbers for which I am allowed to plug into the arc cosine function. But then I have to a little bit worry about what comes out of the arc cosine function, because I can't take the tan of just anything. In fact, you know, if you know the graph of tan, that it looks like this. Well, maybe the graph is kind of the wrong way of thinking about it. I don't know, but I certainly I can't take the tan of pi over 2 or negative pi over 2 or a bunch of other things, right? Tan is y over x, and so those points there are going to crash the tan function. I cannot take the tan of pi over 2. So since I can take the tan of pi over 2, that is the number I need to worry about, because as we've discussed, even way up here, oh man, this is very long-winded, but as we've discussed way up here, on this unit circle, I'll draw it again a little bit bigger, arc cosine always outputs something between 0 and pi. And so it's only the numbers between 0 and pi that are coming out of this arc cosine function. And so there's only one number between 0 and pi that tan doesn't like. The one number between 0 and pi that tan doesn't like is pi over 2. And so here there's like a kind of a warning that I need to make sure that tan doesn't accidentally eat pi over 2. And when will tan eat pi over 2? Okay. Arc cosine of what, so to speak, is pi over 2? Answer, 0. Okay, so just to put that now in chronological order, if x is 0, then of course x over 2 is also 0, and then arc cosine of x over 2 would be, because the arc cosine of 0 is pi over 2, which then when plugged into tan would crash it. So that is why x can't be 0. And so using sort of using my knowledge of tan and my knowledge of arc cosine, I have determined once again that x has to be between -2 and 2, and also that x can't be 0. So the domain is, once again, you did not have to do this both ways, but if you should happen to have tried it one way or the other, then you should get the same answer both ways. Okay, that was like 15 minutes to do one problem, but you can go sort of much faster once you know what you're doing. Perhaps we should skip 9 and go right to number 10, because number 10 is hard. And notice especially that here in number 8, we drew both pictures, but it turned out that we got the same thing in both answers. Well, maybe I should do number 9. Maybe I'll do number 9, but like really fast with sort of minimal commentary. Let's do that. Okay, might as well, right? Number 9, secant. What is the secant of the arc tan of 3x? Chop chop. And yeah, once again on your paper, it's presented as a function. The directions are express this as an algebraic function of x and give the domain. Okay, very fast now with minimal commentary. I'm going to make one picture where x is negative and one picture where x is positive. So here x is negative, here x is positive. Okay, and I'm going to analyze this separately in both cases. Well, knowing things about arctan, if I take the arctan of something positive, it's going to be a first quadrant angle. If I take the arctan of something negative, it's going to be a fourth quadrant angle, specifically a negative angle. So here is the x is negative case, here is the x is positive case, and so let's label the sides of the triangle. Well, let's do if x is positive. Then I need the arctan to be 3x. So the simplest way to do that is just make that 3x and that 1. Now the tan is the ratio between this, and it's 3x. Okay, well then that's just root 9x squared plus 1, and we're good to go. On the other hand, if x is negative, what should I do? Well, it's just not that hard, right? Because I just do this. And now the picture makes sense because, of course, my vertical component is going to be negative. X is negative, so 3x is negative, so the picture makes complete sense. And again, the Pythagorean theorem says that this is root 9x squared plus 1. Okay, now what? Now I just go answer the question. What is the secant of arctan 3x? Answer. The answer I get when x is positive is, okay, what's the secant? It's the ratio between the hypotenuse and the adjacent. It's kind of just what secant is. And so in fact I get root 9x squared plus 1. I believe that is right. Let's do a quick common sense check. This is positive. Do we expect the secant of a first quadrant angle to be positive? Yes. Okay, great. Yeah. Okay, over here now. What is the secant of arctan 3x? Now, in the case where x is negative, well, I still read it off the picture. Secant is the ratio between the hypotenuse and the adjacent, so it's still root 9x squared plus 1. Well, I think that's still okay because this is positive, of course. The square root of anything is positive, but also we should just expect the secant of a fourth quadrant angle to be positive because secant is just the reciprocal of cosine. Cosine is the x-coordinate, so cosine is positive in quadrants 1 and 4. Okay, so this all seems to be just good, and maybe what you might be thinking now is, Mr. Rose, I'm getting tired of drawing 2 pictures every time. Do I really have to draw 2 pictures? Because it seems that I get the same thing in both cases. Aha, wait till the next problem. So far, you do. Alright, it gets more tricky or something. So, okay, that's my answer. I have now expressed this as an algebraic function of x. This function, after all, though it seems to be about trigonometry, is actually maybe just kind of a square root function or something. So, all right, great. Last question. What's the domain? Well, I think it's pretty obvious now that the domain is going to be all real numbers, and I have 2 answers for this. Answer 1, dude, just look at root 9x squared plus 1. That's just has domain all real numbers because this is just a polynomial on the inside, and I have to make sure to take the square root of positive things only, but 9x squared plus 1 is just always positive because x squared is always, well, it just is. So the alternative way of thinking about it is to look carefully at the, I guess I should sort of do it in the reverse. If I'm looking at the expression root 9x squared plus 1, then I think it's clear that the domain is all real numbers. If I'm looking instead at secant arctan 3x, well, I should know some things about arctan, and here are the things I know about arctan. It always outputs something between negative pi over 2 and pi over 2. And so what does arctan look like? It's just doing this, right? It's just outputting something between negative pi over 2 and pi over 2. Well, what about secant? Doesn't secant blow up often? Yes, it does. But if I look, so I can take the arctan of anything. If I look at, this is now a graph of secant I'm making. If I look at it between negative pi over 2 and pi over 2, it just looks like this. So secant is undefined at pi over 2, but I'm never quite plugging in pi over 2 into the secant because arctan is never quite actually pi over 2. It's just maybe close to pi over 2. And so, yes, I can take the secant of anything between negative pi over 2 and pi over 2, and that's what arctan outputs. So, therefore, this function kind of cannot go wrong, and therefore the domain is all real numbers. Okay, for me that was fast, but now let's get to the one that I think is actually hard, which is number 10, and yeah. Still try to go a little bit quickly because I think this is, even though this is tricky, we're kind of building up our skills now and getting more and more comfortable with this. So there's less to say. Well, sine of arc secant x. Seemingly so innocent, but this is quite tricky, and if we become experts at this, it will be helpful for us a little bit later. For something else, well, what should we do? Let's make 2 pictures again. So, I go to do that. Making a picture. So just doing the same old. Here I'll consider the case where x is negative. Here I'll consider the case where x is positive. And we'll analyze them separately, being careful in both cases, and everything's going to be great. Okay. Well, if x is positive, in what quadrant is arcsecant? When we made the graph of arcsecant, we took the secant function, which is not one-to-one, and we restricted it to the interval from 0 to pi. On the interval from 0 to pi, it's a tiny, tiny little graph of secant up there. The function is one-to-one. This is just a long-winded way of saying that arcsecant always outputs something between 0 and pi. But also it doesn't exist at pi over 2. But okay, so if that's the kind of part of the unit circle that you should be looking at when it comes to evaluating arcsecant, then I can say with confidence that the arcsecant of something positive will be in the first quadrant, and the arcsecant of something negative will be in the second quadrant. Okay, that's good to know. Here I'm using my my knowledge of these inverse trig functions? Well, now I have to label the sides of the triangle. How am I going to do it? Okay, well, I need arc secant to be x. So what does that mean? I need to label the sides of the triangle in such a way that the secant of my angle is x. There are many choices here, but one choice that is simple is to just call this x and this 1. This seems to just do the job because, well, the secant of any angle is going to be the ratio between the hypotenuse and the adjacent, and the ratio between x and 1 is just x. So this is a honest representation of arcsecant x. Okay, well, if you buy that, then this is just a matter of doing the Pythagorean theorem, and we get root x squared minus 1. Okay, and maybe I'll just kind of push on now and finish it off. So what is the sign of the arc secant of x, therefore, in this case, when x is positive? Well, the sign is just going to be then root x squared minus 1 over x. Okay, looking good and great. Moving over here, I have some trickier things to do, because here now x is negative, and my sort of temptation is to label the sides of this triangle in the exact same way I did over there, by doing like this. Okay, but now this is kind of double wrong, right? Because well, that can't be 1, because the horizontal component of a second quadrant angle just can't be 1. It has to, in fact, be negative. And the other thing that's wrong is that this hypotenuse has length, negative, which also can't be. Well, fortunately, it's double wrong, because now I know how to solve two problems. And that is, I remind you, you're not bound to any one particular labeling of the triangle. There are an infinite number of correct ways to label the triangle. And so if all I need is that the ratio between this and this be x, then I can solve both of those problems by putting a negative in front. Now I have a picture that reflects reality, because here, this horizontal component of this second quadrant angle is negative now, so good. This hypotenuse, since x is negative, negative x is positive. Very advanced concept, right? The opposite of a negative number is a positive number. So now negative x is a positive number, and that hypotenuse is positive. So that's good. But the ratio between this and this is just negative x over negative 1, which is still x. So it all works. So we solved this problem. This is not the only way to do this. Another option is to make this x squared and this x. That's actually, some people really like that. Now this is positive and that's negative, as it should be, but the ratio is still x. So okay, I'm not going to do that one right now because I find this to be more straightforward. But anyway, there it is. All right, now doing the Pythagorean theorem, I get that this is still okay. When you square these, this is still going to be root x squared minus 1. And then, oh man, video's so long. What is the sign of the arc secant of x now? It's root x squared minus 1 over negative x. But here we should be aghast, because we really did make two separate careful pictures, and we really did get, in some ways, two separate answers. This is the right formula if x is positive. This is the right formula if x is negative. Do these formulas make sense? I say yes. Because looking over here, of course, this numerator is positive. Since we're in the x is positive case, this denominator is positive. Positive over positive is positive, so this is a positive result. Do we expect the sign of a first quadrant angle to be positive? Yes. Going over here. Do we expect... okay, what's this? This numerator is positive. The denominator, since x is negative, negative x, as we said, is positive. So this denominator is positive. This quotient is therefore, this fraction is therefore positive. Do we expect the sign of a second quadrant angle to be positive? Yes, sine's the y coordinate. So these seem to be right. This formula seems to be right. All it means is that from now on, anytime anyone asks you what the sine of the arc secant of x is, you have to give the following answer. It depends. If x is positive, then my answer is root x squared minus 1 over x, if x is positive. On the other hand, if x is negative, it's root x squared minus 1 over negative x. And okay, you can, just live your life that way, and that would be fine. But some people find this to be a lot of writing or something, so we can use the absolute value to sort of help us, because what is the definition of absolute value? The definition of absolute value is it's just the thing in the middle when that thing is positive, and it's the opposite of that thing when x is negative. So here I am assuming that everyone in this class is very comfortable with this kind of theoretical definition of the absolute value, which essentially just says, dude, if it's already positive, do nothing, but if it's negative, like, make it positive. That's what this is saying. But okay, due to this symbol and how comfortable we are with it, it means that we can actually write this final answer a little bit more efficiently, and we can say that the sine of the arc secant of x is just root x squared minus 1 over absolute value x. And this is what people will normally do, and the reason why this formula works is because this absolute value is doing exactly what this piecewise definition was doing. After all, you can think of this, well, okay, I'll stop there. I think it's clear how this symbol is relevant. Okay, last thing to do is the domain. Oh man, I guess once again I have two options. I can do it using the algebra. If I look at this algebra, I see two things. I see that, of course, x can't be 0, but also, actually that's sort of not even important or anything, because if x is between negative 1 and 1, we're in trouble, right? Well, once again, x squared minus 1 needs to be greater than or equal to 0, so x squared needs to be greater than or equal to 1. When is x squared greater than or equal to 1? That's true if x is greater than or equal to 1, or x is less than or equal to negative 1. And so just from looking at this alone, even if I didn't know any trig, I would say that the domain of this function is everything from negative infinity to negative 1 union 1 to infinity. And I believe that is just the right answer. Could I do it using facts about arc secant? I suppose I could. Sure. Because what does arc secant look like? Well, it is, using the restricted version of secant up there, secant of 0 is 1, so arc secant of 1 is 0, and that's pi over 2, and we get this kind of like that type thing. But then also, when you plug in negative 1, it's like up there, and so you get that. So I hope so, yeah, pi, negative 1 pi, yep. So basically, you just can't take the arc secant of numbers between negative 1 and 1, but you can take the sine of anything, and therefore this is the right answer right here. Okay. Woo! Good. Scared to see how long this video is? Oh yeah. Alright, goodbye class.